Thanks everyone for coming. Today we are honored to host Ido Dagan. He is a professor at Bar-Ilan University. He has many prestigious titles and has done many things over the years. For example, he was the founding director of the Bar-Ilan University Data Science Institute. He is a fellow of the ACL. He was the president of the ACL in 2010, during which he led the establishment of TACL. And he was one of the people that initiated and promoted textual entailment as a task in NLP. His interests are in semantic processing, semantic representations, summarization, and text exploration. And we're happy to host him here today. So I'll give it away.
Thanks, Jesse, for the kind introduction and for organizing my schedule today. And I'm happy to be here. So today I'd like to share with you kind of a couple lines of research, my major lines of research these days. And I kind of chose to pack them together under kind of a unifying theme of decomposition or decomposition approaches in NLP. And as in NLP, we're mostly doing modeling on one hand, and representation. It's maybe one way to look at NLP, a combination of AI in general, models and representations. I'd like to talk about decomposition aspects of this decomposition in both. Okay. So, and I mean, obviously, what I'll be talking about are concrete works along this kind of that fit this perspective. So it will be the bulk of my talk, but I try also to inject kind of a broader perspective, of decomposition. So from kind of, so just I added one slide of like broader perspective or motivation for, let's say, giving this angle to my talk. And well, it's not in my talk, of course, it's also an angle that I have on my own research. I mean, we all know that recent years, with the whole deep learning kind of the surge of deep learning technology, which is extremely powerful and helps us do things which were kind of dreams just a few years ago. But we know that it kind of pushed us as a community to develop both models and representations that we understand less and control less. I think people that have been around before the deep learning wave would agree with it, right? And particularly, it's hard to understand control, what you're doing when you're doing something completely end-to-end, which is something that the deep learning technology allows us. Usually before deep learning, we couldn't really do things completely end-to-end. We couldn't just fill in the input, output, and we are done some huge model, and we were done. So that's one aspect, which is, I mean, at least by scientific tradition, is not so desired, right? Science is about understanding what you're doing. And also, I mean, I think we all know that when tasks get complex, challenging, or we don't have training data, so under various circumstances, it seems that the completely kind of uncontrolled black box or less controlled black box approach kind of might be putting also some glass ceiling on performance that it's harder to figure out how you might further integrate systems. So that's kind of, I think, it is nodding, so possibly either there's no end-to-end religious people here, or maybe there is, or maybe they're polite. But anyway, and of course, if you start thinking, how can we regain some control? I mean, assuming we're not going to throw this model anywhere, and we all want to use them, but how we can regain some control, the aspect of decomposing both kind of your models and representations might give us some kind of handle on that from a couple of perspectives. On one hand, if you kind of decompose your representation, so whatever you expect to, let's say, represent in some embedding space, or your model, so whatever the scope of a particular task you give to your kind of black box deep net, in a sense, I mean, there are two aspects of getting some control over it. On one hand, because you decompose, you have some control or some kind of control points between the components of your model, figure out what's happening in each component. And also, in a sense, you're narrowing the scope the challenge you put on the black box component, because you give it, the task of representing maybe a simpler information unit or addressing a simpler, smaller task, and that might also ease performance, reduce the challenge on the system, so it might be more trustable, more reliable. So from this perspective, decomposition might be a way that might give us some leverage from that perspective of getting better understanding and control. And in this talk, as I mentioned, I'll describe actually two concrete research lines of my own group. One of them will focus a bit to illustrate how we might decompose a task to several subtasks in a way that might get us some advantages. And specifically, I'll talk about our work in the use case of multi-document summarization, which is indeed a challenging task. And many people actually, some people address it end-to-end, but there are many papers, actually, if you look at the literature of MDS, multi-document summarization, many of the papers also take some kind of decomposed approach. I'll describe ours. And with respect to representations, I'll describe our approach to develop a kind of a semi-structured natural language-based representations where we try to represent information units to question and answers in some kind of systematic way. Okay, and for those who, if some of you have attended or watched my keynote at the NLP, it was 8 months ago, so my entire perspective and research lines haven't changed that much. So there's going to be some overlap, but I think there will be some both new information and some additional. Okay, so let's start with the first one. So decomposed modeling and the multi-document summarization use case. So just the first few slides, this animation, is just going to illustrate the general idea of how we might look at decomposing a model for a task. And then the bulk of this part will be about how we do it for multi-document summarization. But first, just this kind of animated slide about the general idea, right? So generally speaking, and by the way, I guess also if I use, usually prefer using my have the advantage of long hands. So rather than the mouse. So right for certain, and I'm assuming as I'm talking here about, let's assuming a supervised setting, common supervised setting, right? A task instance contains the input for the task, the output. The trained data contain many such instances, and in the end approach, we just feed such instances to an end-to-end model that tries to convert the input to the output, right? However, many tasks, especially when they get complex, do have some inherent substructure. Talking a minute about summarization, salience detection, redundancy detection, text planning, generation, etc. So conceptually, right, if the task does have some inherent subtasks that we believe are real in a sense for the task, we could consider, like in this case, it's a pipeline approach. The flow might not be just a linear pipeline. It's illustrated as a linear pipeline, where we have subtasks, right? And each subtask has its own, input, right, and output, okay? And we may try and develop modules, and because if we have, let's continue the models with the data. This is the data, the secrets of the model. So this model has, let's say, the main input, but has some intermediate output and so on. This model has like this input and that output. We can, if we have such training data, we can develop separate models which have kind of smaller tasks. Of course, a key requirement for that is that we can obtain these intermediate data sets, right? Data sets for the intermediate steps, because usually when you have a data set for a task, you only have the input-output for the task itself. It's not provided. So that becomes a key requirement. But if we can get these, we could, as I mentioned, train individual models on the respective input-output. And the point is, what I'd like to say generally, that often there might be clever ways to derive such intermediate data sets from the original data sets. So, for that, you need some creativity that's specific to the task at hand, to the structure of the task at hand. And before going and showing how we did that for multi-document summarization, I just want to mention that like an earlier work from our lab, that one was, I mean, it was part of it, but it was more led by Yoav and our joint student Amit Mor Yosef. Step by step, a few years ago, in data to text generation, the web energy setup, where there was like an intermediate test of text planning and not immediately moving from RDF triples, like the Wikidata type of triples, to text, even though, of course, other systems did train like an end-to-end model, just gets the triples and produces the text. This work nicely, I think, presented a way to have some intermediate presentation and data tasking. But now let's move to the main topic here. It is multi-document summarization. So in multi-document summarization, right, a task instance, in a single instance, an input is a document cluster. So let's say 20 documents on some coherent topic. The output is a summary, short summary, 100, 200 words. And that's an instance, right? And the dataset is just many pairs of that. And when this is approached as an end-to-end, I mean, this is like a classic right 6-to-6 setup. I mean, in MDS, it requires maybe some long-range transformer, like transformer, for instance, right? That was more faces here are responsible for that. And you can approach it in a 6-to-6 manner, but implicitly, I mean, also with the history of NLP and also understanding of the task, it does include some inherent subtasks like salience and redundancy detection, fusing information, generating the eventual summary text. So there are some inherent subtasks here. And you know, if we approach it in an end-to-end model, somehow the system learns to do all these. Maybe not really in a pipeline approach, however it does it, right? I mean, everything is interconnected. But these problems remain there, and an end-to-end system also somehow has to somehow eventually confront them. And often we see that it doesn't, right? Like if a system, like in a system would, whether end-to-end to decompose, generates, let's say, repeat some information twice, let's say, even in paraphrastic ways, we see that somehow it failed in recognizing the redundancy, right? Okay. So let's see how a typical a decomposed MDS approach, and this slide, you know, is not specific for us because indeed the literature prior to end-to-end methods did follow. I mean, often if you look at all the literature on MDS, you would see various kind of combinations of the scheme that I've shown now. So a typical scheme for decomposing MDS is first, right? I mean, we have this input, right? Like 20 documents here. We want to generate this shorter summary. So the first thing we need to figure out, I mean, think of people doing the task, right? The first logical thing you need to do is figure out, okay, which information you consider as important enough in order to get into the summary, salient information in summarization terminology. Then, because it's a multi-document setting, the issue of redundancy is usually very prominent. So often there's redundancy between the different documents. Some information gets repeated. So maybe we want to take these salient pieces and figure out, you know, that all those, the red, you know, spans here actually are kind of paraphrastic, mean the same thing, and so on for the other colors. So you want to identify that. And once you have identified that, you kind of understand that this is like one unit information, this is another. You want to somehow fuse them, combine information, and eventually generate the text. Okay, so this is a typical scheme for how we might go about decomposing. And yes, to which really inherent subtasks. I think you would agree that these subtasks seem to be really based on our understanding, you know, as scientists. Okay, and as I said, the key requirement is to enable that is to obtain these intermediate data sets so we can train respective models for the subtasks. So accordingly, the two parts that I'm going to describe now in more detail are first how we can obtain, like the clever idea of obtaining the intermediate data sets in the MDS case, okay? And the second, and that was a paper at Cornell last year, and the second is a concrete system, you know, it's like a first version of a system. It doesn't still handle all aspects, but some of the aspects which follows this decomposed scheme and was presented actually last week at Monday. So these are the two parts on this one. So this is the first paper. It actually was one of the two runner-ups at last call, at the Cornell last. Sorry. Okay, so this is the scheme we want to follow, just repeating the slide from before, right? And we want to obtain such intermediate data sets, okay? So the key idea here for obtaining this data set is to look at the concept of aligning propositions, subsentential propositions, proposition, but subsentential like facts between the summary and the source documents. Okay, that's the idea that's going to enable us to derive these data sets. Okay, so let me say what we mean by proposition. So we take here the notion of proposition of being, information conveyed by the predicate and all these arguments. So like, right, the boy went home and ate dinner. That's a proposition. The boy went home and the boy ate dinner. So there might be some overlapping, right? In a sentence might take some propositions with some overlapping segments. Okay. So it's kind of representing a standalone fact, which is a natural unit for the summary. And in fact, this pretty much follows, for people familiar with the pyramid evaluation method for multi-domain summarization, 15 years ago or so, maybe even a bit more, but almost 20, yeah. It was a bit after Rouge, right? And Rouge was like 2002, so maybe that was 2004, yeah. By Annie Nankova. And there also it was shown that actually these kind of proposition units, which were called SCU, Summary Content Unit, but it's pretty much the same. We just don't follow the exact annotation guidelines, so we call it propositions. But we pretty much follow that notion. Were shown as a useful kind of information unit to measure, which information is got in the summary. So we can follow that idea. And technically, we use OpenAI. Actually, we use the NLP OpenAI system, which was developed by Gabi Stanotsky as part of his PhD, and then was incorporated by NLP. Just as a technical tool to obtain, there might be other ways to take a text and identify proposition spans in it. Okay, so now that you understand what propositions are, let's understand the idea of summary source proposition alignment. So suppose we have this summary and we identify the propositions. Okay, so these kind of colored spans would be my visual representation of propositions. Okay, so we can decompose the summary into proposition spans. But now each such fact, right, captured by proposition, I mean, because we are talking now here about a reference summary, so authoritative reference summary, must have its counterpart in the source, right? Summarizing something in the source, right? So there must be something in the source that corresponds to that reference summary position, and we'd like to identify that match, okay? So we can basically look at each proposition in the summary and look for its equivalent proposition spans in the source documents, and each one might appear also in more than one document, right? And then we get this scheme, right, that each color span here might have corresponding proposition spans in the source document, one more or more of the source documents, right? So, I mean, this example illustrated it now. From now on, I'll just go with a visual representation. Okay, this way. So now, so first to obtain such a picture in that Connell paper, we actually found a way to derive such kind of silver, let's say even kind of pure silver gold kind of data, because it was derived actually from data sets of pyramid annotations. It was extending some method in the past, you may look at the paper, but we had a way to derive a training data of about 20,000 alignments, which was enough to train a supervised proposition alignment tool called SuperPal. It's on Hugging Face, so which is kind of the first supervised proposition alignment tool trained on summary source data, which is quite reliable data. It's derived from the manual pyramid annotations. So if you need a proposition alignment tool, so it's kind of like a paraphrase detection tool, kind of paraphrase classification tool, you can give it two proposition spans, which are subsentential, and it will tell you whether they are paraphrastic or not. Of course, you can tune special. Okay. So now we have this tool, okay, which is supervised. SuperPal stands for supervised proposition alignment. Now that we have this supervised tool, right, we can run it. So it was derived by some training data. It was trained on some training data of this form. But now that we have it, we can actually take now a large scale MDS dataset, which has this same structure, many on the same slide, and run our tool and get silver level data of such proposition alignment, right? Summary source proposition alignment for a large dataset, let's say like multi-news, which is a large scale dataset for MDS. Okay? So now we can have silver data of this form over MDS, supervised MDS datasets that include a reference sample. Okay. Now having this data, this gives us the power to derive intermediate datasets. And that's what I'm going to show next. So we have such datasets, right? Now, as an intermediate dataset, so I mean, without the colors, it's just a training instance for end-to-end MDS, right? But with these colored alignments, we can actually derive a dataset for salience, right? I mean, what are the salient parts? What are the salient spans in the source documents? It's all the colored ones, right? All those that got aligned with something in the source. I mean, this was an important salient piece of information that found its way into the summary. So if we just take the highlighted spans here, ignoring the color, we get training data for salience. And by the way, similar ideas were already, this is not completely original. This part is not completely original for us because such methods were used in the past for getting training data, let's say for salient sentences in extractive summarization. So similar ideas already were in the literature. So we follow the same rationale, but with the notion of these proposition spans. Okay. Now we also wanted training data for clustering, right? But so all these are salient, but actually if we look back at the colors that we have here from the alignments, we know like that all the red ones align with the red span, the red proposition in the summary. So they should be by themselves, these paraphrastics, right? So all the red ones are a cluster, similarly to each of the other colors, okay? So now we can have a training data which might be used either to train a supervised clustering method, or if we just want to look at the pairs, we can train something like superpar also, which is proposition aligned. Yes, please. And by the way, before, yeah.
Yeah, just to clarify, so for the salience detection, the underlying assumption here is that if a proposition
For the what detection?
for the salience detection
Salience.
for data set one,
Yes,
your underlying assumption is that if I find a proposition that matches something in another document, then that implies it's salient because it occurred in 2 or more places.
No.
No.
All the red ones here are actually paraphrases of this proposition in the summary, right?
Okay,
so
starting from the summary. I see.
Starting
That's how
from
you
the
know it's
summary.
salient.
Yeah.
Right. I was gonna
So I think,
push
yeah,
back
because
and say-
here, right here, some parts are not like most spans will not be colored, right? Most,
Right.
25 documents only, the summary is 200 words. So, but those colored, those that align here means that they have information that found its way to the summary.
Makes sense.
Okay. And as I mentioned, this is, I mean, this one, the answer to it is not an original idea. For us, it was done at the sentence level in the past. Okay, for the clustering, same thing. Now, if we do look at the colors and we track all the spans that were aligned to the same proposition level, same color, then they are supposed to be paraphrastic. Is given this for clustering. And I want to do, let's say, fusion. I'm kind of shortcutting here. We know right now we want from these clusters, we want to generate a summary. But we actually know, right? We know that this is green, right? Or is it like olive? Sure, right. Whichever. We know that these 2 clusters actually generated the information in the first sentence. So we can actually now train, let's say, a seek-to-seek model that gets input these 2 clusters and gets this as the goal sentence that it needs to generate. And similarly for the other clusters. Okay. So now we can train a cluster fusion, a cluster kind of fusion and generation model. And actually, by the same rationale, the data set here, I've put all the text generation phase from clusters to text in one step. But you could think first, let's say, on information ordering, right? Like if we look, so this is just a set of clusters, right? It will detect it in the source documents at inference time. But now if you want to train, let's say, a proposition ordering or sentence planning, we know that this is the first cluster, this is the second, these 2 should go in one sentence, this is the third in a separate sentence, this is the fourth. So okay, and actually this is ongoing work I'm doing right now, doing information ordering, and you can do sentence packing, and you can only then go for the generation. Suppose maybe to introduce discourse markers and let's say coreferences and so on. So you can further break it. I mean, by the traditional steps that you find in like 20 years old text generation papers. So I mean, the nice thing is actually you can reverse engineer the entire summary generation process through these alignments. So that's the trick, okay, from that last year. Once we have that, we can have these intermediate data sets. Yes?
This last part where you're fusing the green and red clusters because they appear in the same, the propositions appeared in the same sentence in the summary. This seems a little bit related to the style of the summary writer. This is somewhat subjective.
You're right, but that's kind of training data, right? I mean, as a single training instance, right, from this particular reference summary that you've had, you can reconstruct a training instance that suggests that, you know, mimicking that particular reference summary, you should generate this sentence by taking information from these two clusters in that order, right? Yes.
Feel free to save this for the end.
Probably will.
Why?
Yes, I will.
It feels like there's something important here about why nobody did this 20 years ago, right? Because one of the big complaints about summarization, as I recall, I didn't really work on this problem 20 years ago, and still don't. But the data, we didn't have data sets like this that broke down the different steps where you could apply machine learning for each of the things in your
Actually,
sequence.
I mean,
But
the
now
superpal, so the superpal, you know, the smaller scale DAC and TAC data sets,
Yeah.
you know, DAC is like started 20 years ago, and I think like about a dozen years ago, it changed, you know, to TAC, right? The summarization moved from DAC to TAC. The pyramid data is actually like from 15 years ago. The pyramid data which we used to train superpal. Now, basically, in the pre-neural time, you know, in the pre-large data sets time, like in the DAC-TAC period, people in principle could have done that over the DAC training sets. So we trained superpal over the years where we had pyramid data, because as I said, the training data was derived from the pyramid annotation, from the human pyramid annotation. But then, like 15 years ago, people could, in principle, train such a superpal.
But what do we have now that made this work now in a way it wouldn't have?
No, the only thing that we use now is that now we run superpal on larger data sets that are available today, like multi-use.
Okay.
But basically, you know, if people were thinking about this 15 years ago or 10 years ago, they could apply the same method, let's say, on all the DAC and TAC years, because pyramid annotation year maybe only on 3 years. And, you know, and maybe the SVM-based classifiers that people use in
Maybe
the
it would have been fine.
that could have been fine. But,
Okay.
you know, I think many ideas are like that, right? Okay.
No, and that was not meant to be a negative comment. It was more, I thought it was
I was
some
thinking
special sauce that we had developed over the past 15 years that we didn't have back then.
No.
Yeah.
Yeah, that
Maybe,
yes,
maybe.
that if I were doing summarization 15 years
thought
ago
you were gonna say
and with different students, probably I wouldn't take that on.
I thought you were going to say that it was because we had pre-trained.
You know, if
models.
you already knew it and already took the, I missed, okay, so just one more credit, actually, I mean, it was, I think, just in the last spring-neural, maybe in Hong Kong, last spring-neural conference, I was actually talking to Dan Deutsch that pointed me to this work. I wasn't aware of it, because I've started working on summarization more in recent years. About these ideas of these summary source alignment that I mentioned already existed in summarization literature for salience at sentence level. And that's what triggered our thinking, you know, so just happened to recognize, that's all. Okay, so now, I mean, the takeout from the last few Conan paper, we can now have data sets for the intermediate. Okay, and now doing that, now I should run quickly. Yesterday, I had a 90 minutes here. But that was academia. So it was pure academia. I worked in the industry for 5 years, but in the startup. Then I chose to go back to academia. So this work from last night is basically taking this idea and indeed using it to develop a concrete system that generally follows not exactly the entire, so it's not exactly by the prescriptions I showed, but roughly following this pipeline and indeed gets, you know, as of knuckle submission, state-of-the-art results on these data sets. So this is the input and output, right? So specifically, and that system is called pro cluster because it's based on proposition cluster. Okay? So the idea is, I mean, the first kind of step is indeed identifying the salient spans, which includes these two steps of proposition extraction using OpenAI, and then a salience detection model. It trains a salience detection model. Then we do clustering using superpal. In a minute, I'll show up a couple of bullets on with a little bit couple of details about the modules, but then we cluster the proposition or parasitic propositions, and also decide about the ranking with respect to salience, because maybe you have 20 clusters, but you want only maybe 9 clusters into the summary, so you need to do some ranking, salience ranking. And then we do one step of fusion. In this system, we generate a single sentence for each cluster. So we don't do this kind of merging 2 clusters into a single sentence. That's not handled yet. And we also don't do any kind of coherence ordering. So like if we do rouge is insensitive, that's not measured. So you could regard the summary in this system more as like a bullet style kind of proposition cluster. Okay, each bullet is like, I mean, we concatenate them, but each sentence is a separate kind of. Okay, so that's the overall scheme. And indeed, for this, I mean, these two are supervised models, and indeed, the training data for the fusion was derived by superpal. Here we also use a bit other mode of supervision. Actually, here we use it in rouge, and the clustering. So we did try both supervised clustering, but also kind of agglomerative clustering, where the supervised part is only the similarity metric, and we use the superpal as a similarity metric. They both work pretty much same performance. Often in MDS, many data see that agglomerative clustering works pretty well for MDS. So actually, we didn't need supervision. We didn't use a supervised version. It's maybe an interesting problem. Not many people work on actually supervised clustering. There are algorithms for supervised learning for clustering. Often they just supervise the similarity metric and then do unsupervised method. But it's maybe an interesting way to task to leverage the full power of supervision. So that's the flow of the system. Okay, pretty much following what I mentioned before. You can see here examples, right? So we get the clusters, and then using the fusion model that was trained, as I mentioned, showed in the previous slides. We trained a seq-to-seq model that takes as input a cluster and produces a sentence. And you can see, for instance, here the fusion model. Don't remember if you use BART or T5. You see, generate a sentence that combines spans from two different source propositions in the cluster. So that's an illustration. Okay, with respect to results, indeed, we managed, by the time of Lacan submission at least, we managed to get state-of-the-art results that make reasonable improvements. These are rouge results, so content, automatic content evaluation. And you know that in rouge, like, difference of 1 point is actually quite substantial. These are the results. There's still much room for improvement. This is kind of an oracle summary that picks at the reference summary and tries to see which kind of proposition spans could be inserted. So you see there are still large gaps, so there's room for improvement. I didn't mention that. We have both an abstractive and extractive version. So the version I showed before on the slide was abstractive. Extractive means just instead of doing the fusion, it's picking a representative proposition from each cluster. That's the extractive one. And actually, as was seen here, that in many papers, in most papers you look at, you often extractive versions suppress abstractive with respect to rouge, with respect to content, because kind of the more exact abstractive tends to be. In our case, actually, this method, we got better results in abstractive. And I'd like also to point out, if we look at the outputs here, so when the task is not really generating summary sentence when taking 25 documents as input, but giving it a rather restricted cluster, the system tends to do something that also other systems do. Is often, even on the abstractive system, what it does actually is kind of copying right spans from the source and gluing them together, which I think is the better thing to do these days. Because just a side note about summarization, oftentimes you would see like abstractive as a kind of sacred value. Wow, it's much better. It seems much more intelligent if it abstracts, puts new information. But often we know that actually leads to hallucinations, and it's not necessary that the model is better. And if you have the piece of information that you want to you identify the piece of information, and you have it nicely written in a source document, why not leverage that to your summary, right? So I think actually the more promising, let's say in the near future at least, before we have, magical abstractive methods that can avoid hallucinations and maybe do some abstractions. Right now, we don't really get, NLP model don't do real abstractions, like abstracting idea. Doesn't work. So I think for now, actually, methods that try to combine pieces and just glue them together properly, doing more like discourse are more promising at this point. And it seems that's what a model, a T5 model does when you give it rather narrow input. That's just a side. Okay, so these are performance and also in manual evaluation that are expected in summarizing paper. Also, pro cluster, it provides performance. So this is the previous, ablation results. I'll go quickly, but basically show that each step, it's better to work with propositions than in sentences. It's better to add clustering. It's better to add fusion. Okay, as I mentioned, fusion works better than extractive, actually. And these are the main takeaways, okay, from the ablations. Again, I'm rushing a bit. Now, the last point I want to tell about this work is that I started with the motivation of getting more control and more understanding of what's going on. And indeed here, right, we can examine what's happening in each step. And I'd like to illustrate how in this paper we actually propose leveraging it for two kind of useful properties or feature. So the first, right, because we can track the summarization process, the first is we can actually offer for like an applied setting that showing the user the clusters, the original clusters for which a sentence was generated, can be a useful feature for the user because it can enhance some more information because the cluster might include a few more details that didn't find their way into the summary. And the user can also verify and assess, okay, what's the source of the information, then also expense. You can imagine, like, if this is a summary, you can imagine a user, like, say, double-clicking here and getting to see the entire cluster, so they can see verified information, get some more details, maybe clicking here and then getting a broader scope, right? And this is something we can track in this system because we know exactly by design that this summary sentence originated from this cluster. Okay, so we provide. In an end-to-end system, it's much harder to track. I mean, you may do various tricks and maybe it's alignments or whatever, but here it's, you have it readily available. So that's one aspect. And the other, using the same idea of that what's the source for each summary sentence, like a narrow scope source, which in the form of a cluster for each summary sentence, you can also evaluate faithfulness. So if people are familiar with summarization, in the recent years, there's been some data sets like Frank, others, in single document summarization, where in order to address hallucinations, they let people annotate data sets where you see the system summary, you get the source document, and people have to annotate whether the summary sentence is faithful or not. Okay, so this is like manual annotation or evaluation of faithfulness, which people, knowing that systems are not faithful today, you'd like to evaluate and measure. But nobody did that for multi-document summarization, right? Because that's hard. You see a summary sentence in a multi-document summarization, asking an annotator to look at 25 documents and verify whether this is correct or not is very tedious, right? In our case, it's much easier, right? Because if, let's say, we want to verify this sentence E, we know that by design, this sentence E was only generated from this cluster and nowhere else in the 25 source documents, okay? So we can just show the annotator this cluster and let them verify whether it's faithful or not. Here you see an example also of hallucinations in this cluster to sentence generation. We use, standard 6-to-6 model, and we see that the summary thought it's Hansening accused, but actually it's the UN that, I'm sorry, summary generated that the UN made the accusation, but actually it's Hansen that made the accusation. Okay, and we indeed included in the paper such an evaluation which show that there are like 15% of the sentences are hallucinated, which is, I think, we don't have results, comparable results, but we know that often it's like in the 20s or even 30% hallucination. So it might even be that having a narrow scope reduces hallucinations, but that has to be investigated. But the point here is we could include such evaluation for the first time for MDS. Okay, so that's the general idea. To conclude, with respect to MDS, we have these ideas of decomposition and clustering the proposition level. It allowed us to get the state-of-the-art results. And the last part I mentioned, which I think is very important, it kind of illustrates the additional power, the additional kind of explainability or understanding you get from this decomposition. Okay, and from a broader perspective, it's what I said at the beginning, right? Potential of task composition and the idea of being smart on deriving intermediate answers. So that's so let me now go a bit more quickly. Yeah, 20 minutes. That's about proportionally the smaller part to the second part. So now I'd like to talk about decomposing representations. Okay. And this is kind of a research line we've been pursuing for about 5 years. As you'll see in a minute, it kind of originated with the ideas of QA-SRL, if people are familiar with this work. And then its collaboration line with Luke's group, particularly with Luke and Julian Michael. It is now graduating, and we have quite a few papers with them along these lines. And then the other students from my group. So I'll go quickly over those. I mean, so similar rationale you could think about decomposing a model is relevant also for representation, right? Because if you have an end-to-end neural network, in a sense, the presentation is, all the vectors generated along the way. I mean, you might look at the embeddings from the last layer or whatever, but basically the representation is right. All the parameters you get when running a certain instance. In the old times, right, we did use to extract explicit features, right? So we had some intermediate representations fed to machine learning models. Nowadays, all as I mentioned in the parameters. And again, we might ask similar questions as we asked about models, also about representation. Can we get better understanding, better control, better explainability, and maybe better performance in certain cases by gaining better control through some kind of explicit decomposition. Okay. And now, but the question now becomes, okay, if I do want to, and I'm talking more semantic information, so I'm looking, most applications, right, most applications in NLP are about the information in language, in text to speech. So I'm more interested here in semantic structure and the question which ones we should use. And just making the connection to the previous talk, also in the previous part, the first part, also there we had actually a decomposed representation, right? Because we didn't regard the documents just as a long sequence, like concatenated 25 documents, just one long sequence, but we actually identified the propositions. So the propositions there were actually a decomposed representation of the meaning. These were the units that we could track along the way. But here, in this kind of QA semantics, I'd like to argue that actually the propositions we used in the first part may not be the ideal or the best fit for a decomposed representation, roughly speaking, because this proposition space included a predicate in all its arguments. But if you want to decompose information, maybe, for instance, summarization, maybe some arguments you would like to put in the summary and some notes. And in the previous work, we didn't track it. Okay. So if you look at, decomposed representation, right? I mean, the NLP literature, I mean, we had smart people in NLP also before neural networks were invited, and and there's been a long tradition, and also smart linguists that inspired NLP people, right? Basically, the line of work in NLP that talks about decomposing information is semantic representations, right? Like look at things maybe nowadays. Because if you look at Merkel, the semantic representations maybe showed up in not in that many, but in the largest number of papers, probably AMR. So I'm giving an AMR example. Right, you take, let's say, this sentence, right? I saw Joe's dog, which was running in the garden. So you have, some kind of, in this case, it's a tree. Generally speaking, it's a graph, right? That talks about that I saw a dog. There's a relation between the seeing and the dog and the running in the garden, and the dog and Joe, etc. So basically, it's a representation that kind of decomposes or represents each individual semantic relation, which is actually an atomic assertion, right? Like a minimal assertion within the sentence, represented as in this kind of graphical representation as a single edge. semantic dependencies, if people are familiar, also have basically the same approach, and it always comes from, if people know the history, the neo-Davidsonian kind of representation that kind of broke an individual kind of proposition per each predicate argument or each individual semantic relation. Okay, right. The fact that I was the seeing person, that's kind of an assertion. That what I saw is a dog is another assertion, right? Might be that the truth is that John saw the dog. Okay, so each such relationship is a single assertion. So that's nice, and indeed, by the way, this is Faye Liu, I was now in Florida in her PhD.
No, postdoc with me.
2015. No, I mean she's now in Florida, right?
She did the work during the postdoc.
Yeah. I mean, who is now? I said who is now? Yeah, but yeah, this was in the postdoc. This was the 2015 was the postdoc, not the PhD. Okay. Thanks for correcting me. I had in mind there was a PhD. Okay. So do you remember?
Of course.
I was assuming I didn't question it. So the idea was actually for multi-document summarization. So I mean, we found this is really an inspiring kind of maybe a little bit preceding its time with respect to the available technology. But as idea, I mean, the idea here was exactly the same, like breaking the information into its individual pieces, matching across documents, and then synthesizing its back. Okay. But I mean, when we look at these traditional representations, right? We know that they rely on what I call pre-specified schemata, right? These are formal representations that take text and generate an explicit decomposed structure that is formal in the sense that it's not text, it relies on some formal schema, okay? Like AMR relies on semantic roles from ProBank and verb senses from VerbNet and so on. So these are like formal structures, right? And we have formal structures, I mean, we have these perspectives, that these schemas differ, so there must be some arbitrariness. They require expert annotation. They are hard to work with, also hard to understand by actually downstream developers, right? With users and system developers and NLP researchers. There are not many people in the community that can interpret the labels.
You did your PhD after 2015. This is like Greek.
Yeah. Okay. And we see here the example, like just for the different, let's say, role labels between ProBank and frame, just as an illustration. So we kind of, and I mean, I must admit, I personally, I mean, you could know it was mentioned, we started kind of the textual entailment, and the whole motivation was for textual entailment was that to have something that's theory neutral, because before that, entailment was only kind of evaluated or addressed computationally under particular logical formalism by formal semantics, and it was quite very niche. And the idea with entailment, it phrases the whole setting in a pure natural language setting. And that's, I think, I mean, I always have these worries or kind of alerts when I see a certain taxonomy that kind of commits to a certain particular formal way to view the world or the language. And I always tend to look for the more kind of natural language-based ways to look that are less committed, more theory neutral from that perspective. So if you look into that, so that's the inquiries, and that's a problem with the older this time traditional schema-based methods, and we know that this really hinders their utility and it doesn't catch up, right? An alternative is to use some structures that, even though they have some structure, internal structure and explicit structure to them, they're based on natural language expressions. So the most typical, I mean, the most prominent example is OpenAI, right? It has some structure, it's tuples, you have these commas, right? But the fragments are natural language spans. That's it, right? And indeed, just last year, people tried to leverage such representations, build OpenAI-based graphs, so they translated these tuples from the whole text and use it for various purposes. So people are trying to to leverage these structures. But they have some limitations. OpenAI, particularly, doesn't tell you anything about the argument, okay, except its position. But the position in the tuple is not consistent. You can see that, like, if the original sentence order would be different for two equivalent sentences, we'll get different structures, which is, of course, not desired, and we don't know what the role of each structure. Okay? So, what we found as kind of inspiring is this work that started with the QA-SRL development back in 2015 by Luheng He, joint work with Luke. And the ideas there was focused on SRL, semantic role labeling. Right? Semantic role labeling, you need to identify, if you do prop bank SRL, Obama was born in Hawaii, this will be arg0, this will be arg-log, this will be arg10, okay? But we know that kind of the colloquial way to refer to semantic role labeling is that semantic role roles answer, you know, who did what to whom, why, when, and where, etc. So they said, okay, let's just, I mean, the slogan there was, let's annotate natural language with natural language. So if actually these roles answer the question, let's just annotate these questions. And the annotation they created for this born predicate was these three question answer pairs. Who was born Obama? Where was someone born Hawaii? When was someone born? 1960. Okay, so that was the idea. We replaced kind of a formal set of labels with natural language question answer pairs that are well understood. Okay, and this was designed for capturing semantic codes for verbs. So basically, you know, the scope of prop bank, let's say. And then the kind of the observation that we had is that actually, I mean, okay, so it gives us SRL in a natural language kind of representation, but actually it also represents the information in the sentence, right? If I would hide the original sentence and just show you these three question answer pairs, I basically convey to you the same information as in the sentence. You could reconstruct this sentence or a paraphrase, right? So information-wise, this is actually a decomposed representation of the original sentence, okay? But the point is that just SRL is not enough. So if you look at a more complex sentence, right, I mean, it has two verbs, last and held, and this will be the QA-Sem output, okay, these four questions. But they don't capture the entire information because there are also additional predications in this sentence that are not verbal. We have, for instance, nominalizations, right? We have trial and release, right? So you can ask, what was trialed? How was something trialed, right? So these are also questions that are, right? Each question answer is actually a single proposition. I mean, if you compare it to the original, like AMR, right? Each question answer captures the same information that's on a single AMR edge, roughly speaking, okay? But these are like edges connected to nominalization. So we'd like to get these as well. And indeed, we had the work a couple of years ago that we annotated data set, like the QA-Sem data set, but for nominalizations, okay? There's ongoing works for non-compounds and adjectives. They also assert various predications that add more question answer pairs to represent the information. Valentina did the work on QA discourse a couple years ago, where actually, if you think of it, in NLP tradition, we have semantic role labeling as a separate task, and discourse parsing, PDTB or RST, as a separate task. But actually, discourse relations, many of the discourse relations are also informational in the sense that they assert a certain information, like here, right? What is the result of the car battery not lasting? The public service will not be held as planned, okay? So this is like a certain predication, right? That something caused another thing. It's expressed by the original sentence through the discourse structure. In this case, there is a therefore discourse marker. There might not be a discourse marker. Sometimes it's implicit, but it also captures some assertion of the sentence. So if we take all that together, right, we can translate this sentence to these dozen QA pairs. And again, if you read these dozen QA pairs, you're able to reconstruct the information in the sentence. Okay. So the idea, and as I mentioned, this set, right, to a large extent is equivalent here, right? Roughly speaking, each edge here, which asserts a certain proposition or certain fact, would have a corresponding QA pair. Okay, so I'm getting, there's more details here. Maybe one detail I want to point out that notice that it indeed can be, I mean, the question answers, like prop bank, for instance, captures only what's called explicit argument. So when only captures predicate argument relations when there is a syntactic relationship. If we see here, like the trial, the nominalization, it said despite successful order, the giant car battery doesn't last beyond, etc. There's no syntactic structure that suggests that the thing trialed was a giant car battery, but it's clear from the pragmatics of this sentence, right? So the QA approach allows you, but people, when you let people annotate QAs, then they don't care, right? I mean, don't track the syntax. If there's something, they read something out of the sentence, they generate a question. Okay. So altogether, we have this series of projects where we annotate QA pairs and we train models on these data sets. Yeah, and as we say, I mean, the advantage of this representation, just finishing the comparison, right? On one hand, we do get these edges, right? These AMR edges. So we can, for instance, if you want to check salience, we now can train a salience model for QAs. We can decompose the summary, align the QAs with the source, and develop a model that can us not just for complete propositions that they are salient, but for each individual predicate argument relation, whether this should go into the summary or not. Okay, so we really get kind of a handle on an explicit handle on the fine-grained level of information. On the other hand, it's all natural language based, so it's easy to annotate. All annotations were done by crowdsourcing, no expert annotation. It's controlled crowdsourcing, a bit more involved crowdsourcing, but crowdsourceable. And they're understandable, and most importantly, right, these are natural language objects. We can feed them into our pre-trained language models and expect much better encoding that if you encode, let's say, by a language model in a linearization of an AMR. So I think the nice thing nowadays is that we have the powerful language models for handling natural language objects. We can do a lot of inference over natural language objects. So that's another advantage of having your representation based on natural language, because then it's amenable for language model. Okay, so I'll skip this one. These are all the models. We recently released a tool, says here V1. I would call it maybe V0.7. So if you are interested, but we have something that now combines outputs for verbs, normalizations, and discourse relations. We will add soon adjectives and take a few more months to add the nouns. There is a demo. You can play with it. You get a sentence, you get this set of questions, and of course, I mean, I didn't scroll, but down there it's the JSON. I think so that's ready to use. We also convert to OpenAI. We have some indications that maybe it even generates better OpenAI kind of instructions, but it's not evaluated yet. It's just an option if you'd like to use it. And I think the last thing I wanted to say about this is that really, now that we have the tool, we are actually in my group, we are shifting now to the phase where we start leveraging these representations. So, I mean, as you can see, it's kind of a long-term project because you have to figure out how to systematically get people to annotate for you these question-answer pairs. I mean, there were many challenges here. It was a few years, kind of a leap of faith on our side that it's worth the investment. But now we are really moving to the phase where we start leveraging that in downstream tasks like information fusion or faithfulness evaluation and the kind. And I think actually it's very good timing because we started with that like 5 years ago following QSRL. But if you look at the last couple of years, in the last couple of years, actually quite many people, I mean, there's an emerging line of research that actually tries to use question-answer pairs as intermediate representation. That was used, I showed him, so maybe I'll just skip. So people, if you know the QG-QA method that to check faithfulness, generate question answer from a summary, answer them based on the source, and see whether the answers match. If they do, it's faithful. If they don't, it's suspected as unfaithful. And another very recent work by Narayan is from Google. Narayan is the first author, Ani Lewis and Miriam Lapata, Dipanjan Das. I mean, it's from that group that uses QAs for text spanning in multi-document summarization. So they also try to first generate the set of QAs and then they generate the summary from these QAs. So actually, we now see that people are fond of the idea of using QAs as a natural language kind of intermediate representation for various downstream tasks. And I think there's a lot of potential. A lot of potential for doing that. I mean, that's a risk of when inviting me to give a talk. Never finish when I can find. But that's the last one. So I think, but the point is that these, all these methods, so I mean, these methods that popped up in the last couple of years, they usually rely on question generation based on, let's say, training on a squad data set, a question generation model. And the questions you get from that are not a systematic representation of all the information. They capture some, they miss other, okay, they skip some details. It's not a systematic representation of the entire information. Accordingly, like if you do faithfulness evaluation, your method, for instance, is capable of checking some mismatches but missing others. The QA-semantic approach that I suggested is a systematic way where we kind of try to elicit from annotators, I can't say the complete, but a very comprehensive set of question and answer that really captures, aims to cover all semantic representation sentences, similar to traditional semantic representations. And we also made like comparison with ProPeg. I mean, the coverage of QSRL relative to traditional semantic representation is very good, and actually there's more coverage on the implicit side because the question answer approach really lends itself for capturing implicit information. Then your model also captures implicit information. So I think that's the promise. So the bottom line is that we can get here, we can get back into some explicit decomposition that, as you see, other people are looking at also right now, and this might give us a handle, kind of a revisit of a decomposed representation approach that's kind of suitable for these days because it's kind of midway. It's not completely opaque in the model parameters. We have some handle on information, but the elements are natural language expressions that are not kind of committed to a certain theory and are amenable for our language modeling systems. So yeah, and this is like repeating what I said at the beginning. So thanks for listening.
Thank you. I think so we're a couple minutes over time, but we can maybe have, if there's one question or if anyone in the chat has questions, you can just type that in. And then maybe in a minute or two, if anyone has to leave now, feel free to go. Of course, if you have other things, go for it. But we can have a minute or two of discussion.
Yeah, I had a question.
I'm also around for lunch, I guess.
Yeah,
so maybe people
absolutely.
can join lunch if you want to a bit more.
Yeah.
I had a question on like the kind of answers that are they extractive or can they be like yes or no answers, the answers to these kind of questions that you use to represent this in letters. So
If they're what? If they're
are they all extractive questions or do they
the answers?
Yeah.
Yeah, the answers are typically extractive, sometimes up to a little bit of editing, kind of polishing, but largely speaking, mostly speaking, they are extractive.
I mean, you could see yes or no to be a case, right? If let's say you have a sentence like John was born in the United States and does not have a driver's license, right? You could have like two kind of questions: who was born in the United States? For which the answer is John, and then the next question would be: does John have a driver's license? And the answer to that is yes or no, right? But
Yeah, so actually, it's a detail that I skipped, but one aspect that's captured by the questions, and it's not completely, even though it's not completely systematic right now, is actually factuality. So in this case, the question will be, who does not have something, John? Okay, so actually the question will be, I mean, the question template does have the modal in there. So, it might be positive or negative or actually uncertain. So who might have a dry sentence? Like John tried to get, so to have the driving license, so the question would be who might have a driving license. So the modality of yes, no would be captured in the modal of the language structure. That's how the questions look like. It's not completely systematic. So, I mean, the models, I mean, it's still something for future work to really work it out. But we point at the fact that actually questions can encode more explicitly additional aspects like modality, factuality, things like tense. Okay, so I think there's room for further research to further refine what we can get out from the questions, actually.
Any more questions?
I might ask.
Yeah, go for it.
It's a very great talk. I don't work on summarization, but I learned a lot. I think what you refer to as how much you cover the information and how faithful it is, I almost view it as like precision, and we call it the salient information. Right, so there's a precision we call it what you want to include, and there's the fluency of the summary. So where do you think is the biggest challenge at this point?
With respect to in the summarization case?
Yeah.
Yeah, well, I don't think we have, I mean, there's room for improvement in all models. I think nowadays, if you just look at kind of the output of summarization systems, they are not that bad in salience detection. So salience models trained this way are fair enough, to give me some information. And with the new, the current text-to-6 models, also it looks fluent. So maybe the most burning issue with current summarization systems is indeed the hallucination, the faithfulness. I think if that one gets solved, let's say in the next few years, we'll start seeing many more summarization systems out there, in applied systems. Right now, companies are holding back on releasing this because of the hallucination. So I would say this is maybe the most burning kind of need for summarization. I think maybe I've I mean, the other thing I think is very appealing. I mean, I covered it in my keynote at NLP. I mean, I very much believe that here in summarization, as well as in other areas, the real way to go is interactive systems, which was just the theme of NACA, right? So I'm in good company in these views, right? And we work on interactive summarization. So we had a paper last year. We had actually also a paper last week at NACA, kind of with a reinforcement deep learning model for it improves interactive summarization. The other aspect I think is learning how to interact with users to better to get better kind of information gains for the user and more personal.